be a very exciting part. It's because we are going to check the assumptions based on our data. So we have here written 5 assumptions. We have no autocorrelation, we have linearity of residuals, then we have the normality of error terms, no heteroscedasticity, and we have no strong multicollinearity. So we're going to have them one by one. But before we have each one of them, we need to have the preliminary things that we need to do. So we first have to check whether or not there is really great or higher multicollinearity. And also we have to check first the trend of our data based on the different coefficients. So let's start first by doing this one. So we're going to do encoding of the categorical columns. So let's first have this one. Let's execute this. All right. And then here in this case, we divide the data into two. The first one is for the categorical and the second one is for the numerical column. So let's execute this. Then let's see what these categorical columns are. So we have the customer, state, response, coverage, education, marital status, gender, location code, employment status, policy type, and so on and so forth. So what are these columns that we need to drop? So we have the customer, and then we also have the month. So we don't need them. So we may as well have to drop them. So let's do this. So they are already dropped. Now, what we will do this time is let's do the label encoding of our data, particularly the categorical column. So we use here label encoder. So let's execute this one. So as you could see, we have converted or transformed the different values of the columns into label encoder or label encoding. So there are actually a lot of techniques. So you would be able to convert categorical variables into numerical features or numerical variables. You have enough time, so please study those things. So you have to differentiate between the label encoder and the one-hot encoding. I'm going to leave those things to you because I believe you have enough time for that. So this time we will just do how they are applied in a certain data science project. So as you could see, for the location code, for example, we have 1 and 0. Marital status, we have 1, 2, and so on and so forth. Okay. So now, this time what we're going to do is that we're going to combine the dfnum and then the dfcat. So this one, which is already transformed into numerical features, and also the dfnum, which is already a numerical feature. So basic is the idea in data processing and applying the algorithm to the model, I mean to the data, is we need to transform first the data into numerical columns or numerical features. So let's do this. And then we have in here both the dfnum and the dfcat in one data frame. So as you could see, we have the customer lifetime value, the income, and everything in the data. So now what we will do is we're going to do OLS. It's because it's very important for us to be able first to understand the overview of what's really going on in the data, the different characteristics or attributes of our data. So we would be able to do that later on. So first is we're going to install the stats models because we're going to do the ordinary least squares, right? So it's now done importing, and then we're going to, what I mean installing, and then this time we're going to import this one from stats model. So from this package, there is the OLS. Now this time we're going first to drop the customer lifetime value from the X. It's because the customer lifetime value is our target variable or the Y column. So then we're going to fit this OLS to our data. So let's execute this one, and then we could see the result. Now, first and foremost, we have here the R squared, which is actually very important because it talks about the proportion of the total variability that is being explained by the model. So in our case, we only have 0.167 or 0.167, which means to say that it is just 0.16, 0.7 or 17% of our data is being explained by our model. Or in short, another way to say that is only 16.7% or 17%, just rounding it off, of the variability of all of these coefficients. So we have the income, the premium, monthly premium auto, and so on and so forth, going to vehicle size that are being explained by our model. Now, adjusted, it is 0.165. So it's actually lower. Let's see the p-value. So we have these numbers, which are the p-value, and our constant. So when we say constant, it is also referred to as the intercept of the regression line. And these things here, the income, going to the vehicle size, these numbers here are the coefficients of these numerical columns. So in short, if we're going to make a regression line, then we have 54.5365 plus A, which refers to these ones, right? Then X, which refers to any value of this, and then plus our error term. So we have here the different errors. There's this error. Let me find the error first. Okay, these ones. The errors are here. Standard error. So that's how you do it. So it's actually a very long formula of the regression line or regression algorithm or model. So the most important thing here is this, the p-value. So which means to say that when the slope, this one, it refers to the slope, this, it refers to the slope of the independent variables. So we have these independent variables and these are the slope, the values of the slope. So let's have them one by one. So again, the basic premise here is that when the value of the p-value is equal to 0, then it means to say that the value of these coefficients, independent coefficients here, are not different from the value of the slope. So when it is different from 0, it means to say that the slope is significantly different from 0. Again, let me repeat that. When the value of the slope, these ones, especially this one, the value of the p-value, these ones, is different from 0, it means to say that the slope is significantly different from 0. So let's find first which values are 0 in this case. So we have here the value of the monthly premium auto, which is 0, and also the renew offer type, which is 0, and this one, rounding it off, it could be, right? So we have a 3, which are 0 value, which means to say that they are not significantly different from the slope value, which is 0. So let's take first the case of income. So here, the values of the slope varies from 0 or negative 0.006 to 0.008. And this is for the 95% confidence interval. That is, if it is repeated over time. So when there is a repetition of the calculation of the income in our model, then the values of the income can be somewhere between or somewhere in the interval 0 or negative 0.006 to 0.008. So the same is true in the cases of monthly premium auto going to vehicle size. So that means that for one increase in income, let me correct here. That means for one unit increase in the customer lifetime value would mean a 0.0010% increase in income. That is on average. And if it is repeated, then we have the values which could be found here in this confidence interval, which is negative 0.006 to 0.008. So the same story can be also said for the monthly premium auto going to the vehicle size. And another thing that we have to remember is that of the kurtosis in this case. So the kurtosis value is 15.145. So that means it's actually very, very high. We could say that the distribution is too peaked based on the outcomes or the outputs of our model OLS. Then we have these notes, which are standard errors. Assume that the covariance matrix of the errors is correctly specified. And another most important thing is that the condition number is large. This is too large actually, as you could see here. So this might indicate that there are strong multicollinearity or other numerical problems. In our next lessons, we will be dealing with different problems of our assumptions, like for example, the multicollinearity, the autocorrelation, and so on and so forth. So the basic idea why we do this one, the OLS, is that it gives us a summary of what data and its characteristics are being described by these numbers here. Do you want to know more about this channel? Just click these cards. We do have a lot of free data science courses for free, like Machine Learning Essentials, Deep Learning Mathematics, and a lot more. Here, you can always learn an upskill for free.